After talking tons of theory and the formula about the elastic torsion, let's try to apply what we have learned to a practical problem. The elastic motor exerts a 500 Nm torque on the aluminum shaft ABCD when it is rotating at a constant speed. Knowing that the shear modulus G equals to 27 GPa and the torque acting on B is 200 Nm and the torque acting on C is 300 Nm. We want to determine the angle of twist between B and C and C and D. Also, we want to determine the maximum shear stress inside the entire shaft. For the first problem, we sketch this circular shaft by this simplified schema by using the right-hand rule, because previously we mentioned that by using the right-hand rule you can clearly know that whether the torque is positive or negative. Firstly, we draw those two known torques on this shaft. We draw it from A to D like this. Then at point B there is a torque rotating in this way, and you are the observer standing here. Then, by using your right-hand rule, the thumb is pointing to the left-hand side. Therefore, you can write this torque in this form. Similarly, for the 300 Nm torque, as an observer, you are standing here and you are observing this torque. By using your right-hand rule, you can see that the torque can be sketched in this direction. Your thumb is still pointing to the left-hand side. Therefore, you can draw the 300 Nm torque in this way. At the same time, we notice that there is no torque at point A. Besides, the whole system is rotating at a constant speed. That means there is no total net torque on this system. Consequently, there must be a reaction torque, which is 500 Nm acted by the motor on this circular shaft. Notice that although the motor is rotating very fast at this end, but we treat it as a fixed end. You may wonder why the end D is treated to be a fixed end. Although the engine is always spinning at a very high speed, but the problem is that there must be some component that fixes the shaft at point D such that it can drive the shaft to rotate. Now we are interested to the angle of twist between B and C and B and D. To do this, first we consider each of the segments required. For segment BC, by using the double arrow notation, we can immediately know that there is a 200 Nm torque, which is positive, acting on this piece of material. Then you can find the torsional displacement directly by using the formula. One reminder is that the diameter of the circular shaft is not uniform. For AB it is 40 mm, for BC it is 44 mm, and for CD it is 48 mm. So be careful with it, because when I do this problem for the first time, I forgot to observe the difference of the diameter, then I got the wrong answer as well. So be careful with it. The torsional displacement of B relative to C can be found by using this formula. Torsional displacement of B relative to C equals to the torque acting on the member BC times the length of BC divided by the shear modulus, and you divide by the polar moment of inertia of the segment BC. The torque is 200 Nm. The length of member BC is 1.2 meters. The shear modulus is given by 27 GPa. The polar moment of inertia is given by pi d to the power 4 divided by 32. After a lot of simplifications, you can find the torsional displacement is 1.384 degrees. Similarly, for section BD, you have to observe the torsional displacement in segment CD as well. Consider the torque on CD, since this end is already under a torsion of 500 Nm. Then for this end, it must be 500 as well. So the torsional displacement on segment CD is given by the torque acting on this segment times the length of member CD divided by the shear modulus divided by the polar moment of inertia of the segment CD. The torque acting on it is 500 Nm. The length of CD is 0.9 meters. The shear modulus is 27 GPa. while the diameter of segment CD is 48 mm. Therefore, you can find the torsional displacement of C relative to D, which is 1.832 degrees. Therefore, we sum up the torsional displacement of C with respect to D and the torsional displacement of B relative to C. Then, adding the result in part 1 and the part 2, you can find the torsional displacement of B relative to D, which is 3.216 degrees. Part B requires us to find the maximum shear stress inside the aluminum shaft. Notice that although the elastic torsion formula phi equals to TL divided by GJ is given in the formula sheet, sometimes it might ask you some embarrassing problems such as this: maximum shear stress. You might forget it, right? So for the maximum shear stress, it is given by G times the maximum shear strain. Then you rewrite this formula in this way, so still you have to remember those things. But in this problem, there is no radius given, it is just the diameter, so we just put R to be D over 2. Then we rewrite this maximum shear stress into this form, which is TD divided by 2J. Then we're interested to find the shear stress in each segment. For segment AB, there is no shear strain because A is a free end and there is no reaction torque acting on it. For segment BC, it is subject to a 200 Nm torque. Therefore, the maximum shear stress in segment BC is given by TD divided by 2J of BC. Then you do kinds of simplifications. Finally, you get the maximum shear stress is 11.96 MPa. For segment CD, similar manner, we substitute the stuff into it to get the maximum shear stress in segment CD is 23.03 MPa. Compare all those results, we found that the maximum shear stress in the shaft is just the maximum shear stress in segment CD, which is 23.03 MPa.